Hi, welcome. In today's video, I'll be discussing quantum measurements and I will use the Stern-Gerlach experiment to illustrate how it works. As before, let's consider this quantum state represented by this ket psi. This ket psi is already normalized, as you can see by this denominator, and is written in the basis of the operator Sz, since we have ket plus and ket minus with no subscript. We know how to compute the probabilities of finding spin up and spin down along the Sz, Sx, and even Sy, since it follows the same rules. Suppose that the Sz measurement yields Sz equal to minus h bar over 2. In other words, it yields spin down. Then a subsequent measurement is performed to measure the spin component Sx. What are the possible results? And another question would be, what are the probabilities for them to occur? So the best way to visualize it is through the Stern-Gerlach experiment. I'll sketch below a Stern-Gerlach representation for the given experiment. This is the oven that produces the beam of atoms. These are the Stern-Gerlach analyzers, or sometimes called Stern-Gerlach devices, with two output ports for two possible values of the spin component and aligned along the z-axis, the case of this Stern-Gerlach device, and this is aligned along the x-axis. These are counters to detect the atoms leaving the output ports. So back into the question, if a Sc measurement is made on the ket psi and yields minus h bar over 2, and a subsequent Sx measurement is made, we can see that via this sket drawn here, as if the first Stern-Gerlach device prepared the quantum state and the second is placed in the front of the lower output port where the spin down come out. Since our first Stern-Gerlach device prepared our quantum state to be ket minus, we can ignore everything that comes before this point and assume that our initial quantum state is given by, let's say, ket psi prime being ket minus. We no longer need to think on the first Stern-Gerlach device. Answering the questions, as we're measuring the spin component along the x direction, the possible values are ket plus subscript x regarding the beam of particles coming out from the upper output port, and the ket minus subscript x regarding the beam of particles coming out from the lower output port, with 15% probability for each. So let's confirm it through math. The initial quantum state for this case is ket psi prime equals ket minus. We know that the ket plus subscript x is given by 1 over square root of 2 ket plus plus ket minus, and the ket minus subscript x 1 over square root of 2 ket plus minus ket minus. The probabilities can be calculated by these expressions: plus psi prime squared That's the probability of finding spin up along the x direction. In other words, if a sx measurement is made on the ket psi prime, and we also have the probability of finding spin down along the x direction, minus x ket psi squared. We take the complex conjugated of these kets, and then we have the bras, the respective bras, of course, and I'll do it directly here. So we have 1 over square root of 2 for this probability, bra plus ket minus, that multiplies ket psi prime, but ket psi prime is equals to ket minus. If we calculate it, I'll skip some steps. We end up with 1 over square root of 2, but the probability is this value is squared, and then we have half. So of course, if we calculate the same for the probability of finding spin down, we have to find the same value, since we have only 2 possibilities. If one of these possibilities you have half to take place, the another possibility must be half too, as we can see, as we can confirm through this calculation. Through this example, a link was made between the kets that represent the quantum states and the Stern-Gerlach experiment. I hope it helps. Thanks for watching. Bye for now.